Okay, guys. Yeah, uh, just a minute. Yeah. Hello everyone, and welcome to week three of Analog Circuits. This week's content was mostly related to frequency responses of various analog various analog circuits. So before we begin our own content, does anyone has any issues with the content so far, or any problem, a specific problem someone wants to discuss? We can take that up first.
So in the week one assignment, if you take the 10th problem, sir,
Uh,
uh,
so, uh, can you share your screen and show the assignment so that it will be easy for me to take a screenshot of that and discuss it over here?
Sir, are you saying related to the feedback problems in week 3 assignment?
No, no. The anyone. I mean, if you have any doubt, so week three, I think the deadline hasn't come yet, right? Week three assignments. So till week one and week two, if there is any doubt in any assignment problems, that you can discuss. So, Vinod, can you share your screen and show the problem?
how to share, sir?
Is the laptop accessible to you? In the laptop,
It's a mobile phone.
okay. So in mobile phone also, there might be some three dots might be coming, right? So if you
Share
click,
screen is there, sir.
sorry,
Share screen, that share screen is there.
yeah, yeah. So click on that.
Okay.
Yeah, your screen is visible now. So can you zoom into the tenth problem? Can you zoom in a little bit? Rotate your phone 90 degrees. Auto rotation is available, right? Yeah. Okay, now zoom it out. Okay, this is the problem, right? Yeah. Okay, let me take a screenshot and then I'll paste it on my. Okay, now I will share my screen. Yeah, so is my screen visible?
Yes, sir.
Yeah. So it said that the output voltage for the circuit is shown below. So find the output voltage for the circuit shown below. So, this is an op-amp based circuit. Now, first of all, you have to make sure that all the op-amps present in the circuit are in negative feedback. So, what can you say about, so let's say this is one, this is two, this is three. Okay, so what can you say about op-amp one? Is it in negative feedback? So this is the output. From
Yes,
output,
sir.
where does so it goes to the negative terminal, right? So this op amp is certainly negative feedback. What can you say about op amp two?
So also negative feedback.
Yeah, again, through R2 there is a negative feedback, and in op-amp 3 through R4 there is a negative feedback. So that means to say all the op-amps have virtual ground in them. Now, mind it how the signal has been given to this complete circuit. So this is a differential way of giving the signal. So what happens is, now what will be the voltage at this node? So let's
VA.
call no, actually it will be V. So this node is VICM, right? Correct?
Yes, sir.
Yeah. So it will be VICM plus VI, and the bottom one will be VICM minus VI. Okay. Is this clear? This is clear, right?
Okay, sir.
Yeah. It's a completely forget about basically it's a cascade of two stages. You can see it as a cascade of two stages. This is a stage one, and this is the stage two. Okay. Now, if let's say basically since the output resist, what is the output resistance looking in here? The output resistance looking from this side. So it's the output of an op amp, right? So output of an ideal op amp, what will be the output resistance?
Infinity.
Zero.
No, no, zero.
Zero. Zero.
Yeah. So whatever is cascaded after that won't change the output voltage of the op amps, right?
Yes, sir.
Yeah. So what we can do is we can first focus only till this point. Once we find out the output at this point, we can move to the second stage, to the stage two. Okay. So let's redraw only the first part of the circuit. So this is R2, this is R1, this is R2, and what is this? This is VCM plus VI, and this is VCM minus VI. Correct? This is how the first stage of the circuit looks, right? So we have to find out the voltage between this node. I mean the differential voltage. Now that differential voltage later on will be converted to single-ended in the second stage. We will worry about that later. So let's find out. Let's call this as VOP and let's call this as VOM. So let's try to find out the voltages. So what will this voltage be equal to?
VA plus VA VCM.
VCM plus VI, correct? Because again, the op amp is in negative feedback. Similarly, this voltage will be equal to VCM minus VI. Clear?
So after that, I know the answer. Sir. It is an instrumentation amplifier.
Yeah,
What the doubt I got is since it is a VCM means I thought it is a common mode gain, common mode voltage. So
correct.
how the common mode voltage will get amplified in the instrumentation amplifier? So I
The
thought
common mode, okay. So the way to do it, what you can exactly do is So generally, when there is common mode, and this is a simple circuit, so here there is not much to it. But let's say if this was a complicated, much more complicated circuit, so what we do is we split the circuit into two halves. One is for common mode, other is for differential mode. So I will teach you how to do that for this circuit, and then you can apply it for other circuits as well. So first thing first, you know that this is a linear circuit, right?
Yes, sir.
This is a linear circuit, right? So if this is a linear circuit, so superposition principle can be applied, correct?
Yes, sir.
Yeah. So if superposition principle can be applied, so what can we say is that let's assume initially Vi to be zero. Okay. So if the Vi is zero, only VCM we will consider in this. Okay. Is this clear?
Yes, sir.
Yeah. So if we consider only VCM, so what will happen is the VCM. So let's only consider common mode. So what is happening over here is this will be VCM, this will be VCM. Okay. And if both of them are VCM, so will there any current flow from this node?
No, sir. No.
No, right? So if no current flows, so no current flows through this R2, no current flows through this R2, output again will have VCM and VCM. Correct?
Yes, sir.
Okay. So the common mode gain from of this stage, so let's call this stage 1. So common mode gain of this stage is ACM is equal to 1, right? So whatever input VCM you are giving, the same output VCM you are getting. Correct?
Yes, sir.
Okay, other way to solve this problem is basically, since each of these nodes are swinging exactly the same, right? So this is swinging VCM, this is swinging VCM, this is VCM, this is VCM, this is VCM, this is VCM. Correct?
Yes, sir.
Okay, so I can so if even if I connect these nodes, nothing will change, right? Because since if two nodes are already at same voltage, if you connect anything between connect a wire between them, they will still remain on the same voltage, right?
Yes, sir.
Okay, so if I connect it, nothing will change in this. Whatever currents and voltages were there, they will remain the same. So if I connect this way, how can I write the circuit is, so this R1, no current is flowing through that R, and both nodes are VCM. So it's equivalent to a short circuit, correct? So this R1 will go away, and what we will have over here is, if so these R2 come in parallel, right? Both the R2s come in parallel. So basically we will have R2 by 2, R1 will go away. So this will be around this op amp. So the strength of the op amp will become 2x, but since this is already an ideal op amp, so it doesn't matter. And here we will have VCM. So this circuit can be equivalently used in substitute to this circuit to analyze the common mode voltages. So this can only be done in symmetrical circuits. As far as stage 2 is concerned, this can't be done because this is not symmetric, right? Across the input, this is not a symmetric circuit. So here this thing can't be done. But since stage 1 is completely symmetrical, so this can be done. Is it clear?
Yes, sir.
Okay, so basically the common mode gain comes out to be 1 in this case. Now, since this is so So if let's say only input VCM was there, so this will swing at VCM. This will also swing at VCM. So what will be the output at this node? So now we will worry about the second stage, the common mode gain of the second stage. So we have R3 over here, R4 over here, R3, and this is R4. So both the nodes are at VCM, right? We saw it from explain like analysis of stage one, correct? So let's say this is output voltage V out. What is this node? This is equal to
R4
R4
into VCM
upper,
divided by R4 plus R3. The common mode
right?
gain of this one is zeros.
The common mode gain of this is zero. And how do you conclude that? So basically, this comes out to be this, and we see. Basically, what so this is the same node as the negative terminal. So this basically will be equal to R4 upon R3 plus R4. This is equal to so superposition of the resistor divider VCM R4 upon R3 plus R4 plus V naught R3 upon R4 plus R3. So these two gets cancelled out and V out is equal to 0. So basically this makes sure the this particular circuit over here makes sure that the common mode swing at the output of this node is completely equal to 0. Okay. So whatever swing here happens at the common mode, it won't impact the output of this amplifier. Is it clear?
Yes, sir. Yes, sir.
Yeah. So now any other doubt in this? The differential one, how will you solve? So as far as differential part is concerned, that you will do in the following way. So let's again consider stage one again of the circuit. Now we will consider only the differential part. So this is Vi, this is minus Vi. So what we have assumed that now the common mode is zero, only Vi, the input, the differential input, that is Vi and minus Vi are present. So this is how my circuit will look. Okay. Now what can be done over here is this particular resistor can be written like this, right? So R1 by 2 and R1 by 2, correct? Is it clear? So R1 can be written as a series resistance of two halves of the resistors, right? I am audible, right? Hello?
Yes, sir. Yes, sir.
Yeah. So R1 can be written as two halves of the resistor. Now, what will happen? So let's say there was only Vi and no minus Vi. If there was only Vi and no minus Vi, let's say this node voltage was plus alpha Vi. Okay. And if let's say this was there was no vi and there was only minus vi, since the complete circuit is symmetric, what will be the node voltage at this node? Minus alpha vi, right? So when there is only minus vi over here, the node voltage at this node will be minus alpha vi. So if both vi and minus vi are there, the overall voltage at this particular node will be equal to zero. Correct?
Yes, sir. Yes, sir.
Yeah. So if this node is zero, then what can you say about so even if let's say I put a ground over here, that won't matter, right? Because this is zero anyways. If vi and minus vi are swinging at these nodes, correct? So if this is ground, so this circuit can be split in two halves, right? Vi R1, and this will give you VOP minus Vi R1 R2, and this will give you VOM. Okay, so basically what is the output due to Vi? This is Vi times 1 plus R2 by R1, and this is Vi minus Vi times 1 plus R2 by R1, and their overall potential will be 2 Vi times 1 plus R2 by R1. Okay, now this will go to the second stage, that is, and from there you will get the final output. Is this clear? This is clear, right, Vinod? Okay, I
If you
hope.
separate the ground,
Sorry.
if you separate it by ground, nothing it will not affect
Yeah.
anything.
So that's what, right? As we said, discussed over here, this node is zero anyways. So, even if I connect it to ground, this node will still remain zero as it was previously. Okay, so if this is grounded, this can be written like this as well, right? R1 by 2, and this can be written as another R1 by 2. Because if this voltage is zero, the whatever current was flowing from here and whatever current was flowing from here, in these two circuits also the same current will be flowing.
Yes.
Okay, so basically what happens is, so what pointers you can take from this is, whenever the circuit is symmetric and a differential signal riding on common mode is given to those circuits, what happens is, for analyzing the differential circuits, what all common points are there in along the axis of symmetry. If let's say there is some resistor over here that is cutting the axis of symmetry, you split it in R1, half the resistors, for inductors half the inductance, and for capacitances double the capacitances, and put a ground between them and analyze both the halves of the circuit separately, and their overall addition will be the output voltage. And for the common mode, what all is there between the axis of symmetry, those will just get shorted. Okay.
Okay.
Sir, it should be VA into 1 plus R2 divided by R1 by R2, no, sir?
Uh,
Right.
why there will be another R2 over here? That is differentially incorrect, dimensionally incorrect, right? It's just a non-inverting amplifier, no? Okay, so any other doubt in this? Now, this whatever this voltage comes, this you can apply to the second stage and find out the answer for differential gain. Any other doubt in this? Okay, so if there is no other doubt, so we will move further. So, any other question that anyone wants to discuss from assignment 1 and 2?
Two, I have doubts, sir. Assignment two.
Okay, can you share your screen once again? Again, rotate your phone at 90 degrees.
Third question, sir.
Okay, can you rotate your phone at 90 degrees so that the landscape view comes? Okay, I will just a minute. First of all, scroll up. I will take the screenshot of the above part and then the lower part. Just a minute. Now scroll down. No, no, keep the phone at 90 degrees only. Yeah. Okay. Okay, now I will share my screen. Okay, so now my screen is visible, right? My screen is visible, right? Okay.
Yes, sir.
So, okay, and now basically what it says is op amp in question one is used as voltage follower as seen below. Okay, the slew rate given is zero point 0.5 volt per nanosecond. Unity gain bandwidth is also given, that is 1 gigaradian per second. Find the rise time from 90% to 10% to 90% of the output voltage for various inputs that have been given, and the inputs are given as step inputs. So you understand u of t, right? U of t is mentioned over here, so basically it's like uh, so at so before t equal to 0, it's 0, and then it becomes 1, and whatever is multiplied with it, it scales accordingly. So let's say if it is 50 millivolt, 100 millivolt, and so on. So yeah, so this is there. So what is the like, do you want me to completely go through the steps, or you have specific doubt in it, Vinod? uh,
Sir, I know the formula and all, but In the solution, they have given 1 divided by 1 plus s divided by omega t, like that and all they have solved. I don't know how to arrive the solution.
Okay, so basically what happens is, the slew rate of the op amp is given. So this is the maximum rate at which the op amp can operate. What will happen is, so this is kind of the saturation of the op amp, that if the output, let's say, wants to increase at a rate faster than what is given over here, then it will just get restricted to that. So what you need to do is, and this is basically a non-linear phenomena. So what happens is, so there is some unity gain bandwidth of the op amp that is given. Okay. So if unity gain bandwidth of the op amp that is given, what will be the 3 dB bandwidth of this? That will be 1 upon 1 plus S by omega UGB. Correct? So this thing you know, right? The transfer function from input to output. If unity gain bandwidth of the op amp is given, then this is how you will calculate the closed loop transfer function. Is this clear to everyone, or shall I explain this?
How you got this one, sir?
Okay, so basically, what we have been given for the op amp. So let's focus on the op amp only first. So if there is V, so let's ground this voltage and only focus on Vi. And if the unity gain bandwidth of the op amp is given, what does that mean is that so let's say the gain of the op amp is infinite at DC. So the if the unity gain bandwidth is given, so it will be considered, the transfer function of the op amp will be considered as this. So it's omega UGB is given to this. So how will this transfer function look? This transfer function will basically look like this. So at DC, at zero, at DC, it will be, the gain will be infinite. So A will be equal to this. At DC, A will be infinite, which is the characteristic of ideal op amp. But as the frequency starts increasing, its gain will start dropping, and the gain and at the frequency at which the gain of the op amp becomes unity. So basically, the op amp is useful if it is able to amplify, right? So if it is not able to amplify, then the op amp is useless. If it is attenuating instead of amplification, the op amp is useless. So like after UGB, basically the op amp will give you a gain less than 1. So that's what this transfer function models. Okay. Now if the gain of the op amp is, let's say, A of S. Okay. So if you do the math, what you will get is the overall transfer function, the closed loop transfer function, you will get as A of S upon 1 plus A of S. You can do the specifics of this math. You will arrive at this transfer function. Okay. Now, if you substitute this in this equation, so what you will get is omega UGB by S divided by 1 plus omega UGB by S. So if you take omega UGB by S common, so you will get this as 1 upon 1 plus S by omega UGB. Okay. So this is basically the transfer function from input to output. Is this clear?
Yes, sir.
Okay. So what happened now? How does this this is a first order transfer function, right? You can see this, right? There is a pole that has been created, and pole is basically the 3 dB frequency. You understand the 3 dB minus 3 dB bandwidth, right?
Okay, sir.
Okay, so whatever is the UGB of the op amp will become the 3 dB bandwidth of the unity follower. So the transfer function of this unity follower will look something like this, and this will be omega UGB. Okay, so had this op amp be completely ideal, then the transfer function will be 1 till infinity. But since there is some UGB, so after the UGB, it will start dropping with 1 by S. So this is how you get this transfer function over here. Okay. Now, what is the step response to a first order transfer function? Do you know this? You guys have studied Laplace, right?
1 divided by 1 plus S.
Yeah, 1 divided by 1 plus S is the transfer function of this. So basically, what is it like? So what will happen is it will try to do, if the input looks like this, okay, so the input, wait a second. If the input is this, so this is some V in, and so the output will look something like this, correct? Is this clear? And this is because of the first order response of the buffer. Okay, so like if the input is given as some V, so let's consider the first one. So if the input is, okay, let's consider some random this thing, A times U of t, the output will look as A times 1 minus e to the power minus t by t times omega UGB. So this is basically the step response of first order low pass filter or first order pole. I think you guys have studied signals and systems, right?
Yes, sir.
So from signals and systems, you can go and refresh that. So if the transfer function of the system looks like this, then the step response basically will be of this form. Okay. So if this is scaled by a factor of a, it will basically become this thing. Okay. So this is basically it. So what we are interested in finding that whether from 10% of the out. What is basically 100% of the output at t equal to infinity, the output has to reach a. Now 90% of it is basically it should reach zero point 0.9 times a. Okay, and rest of it is basically the first 10% is zero point 0.1 times a. So we are to find out the time taken by the time taken by the output to reach from zero point 0.1 times a to zero point 0.9 times a. So you will use this equation for that. Now what happens is, so where does slew rate comes into the picture? So this is all okay by as far as the transfer function and all those things are concerned. This is all okay. Now, where the slew rate comes into picture is, so let's say, so what is the rate of change of this particular equation? How will you find that?
Differentiating this.
Differentiating, right?
Yes.
So if we differentiate it, so we get dv naught by dt is equal to a times minus t by t times omega ugb. Okay, correct.
Yes.
Okay, now what happens is what will happen is initially, like initially the rate of change will be A, and as the voltage, as the time passes, the rate of change will keep on reducing. Is this clear?
Yes, sir.
Yeah. So what will happen is, like if this rate of change is greater than whatever slew rate is given to you. So slew rate is given as 0.5 volt per nanosecond. So basically, it's zero point 0.5 into 10 to the power minus 9. Sorry, 10 to the power 9 volt by second. If the rate of change is greater than this particular thing, then the rate of change will get restricted to this slew rate. It can't increase. So if the demand from the op amp is more than whatever the limit is, the op amp can't produce any further thing. Okay, but if it is less than that, if this particular quantity is less than the slew rate, then the output will rise based on this quantity. So it's kind of an equivalent of a power supply saturation. Okay, so as the voltage of the op amp saturates, the current also for the op amp saturates. Okay, so op amp can only source finite amount of current. That depends on the internal structure of the op amp, and you will read this, learn about this in some advanced level courses. But the current of the op amp also saturates. So if the current of the op amp saturates, then the rate of change will get fixed to this particular value. Similar to if the demand from the output of the voltage of the op amp increases from the power supply, it gets saturated to that, right? So this is a similar concept here also. So till the time you are in the linear region, you will have this rate. Otherwise, you will have this rate. So now let's see for the first this thing. So basically, it's a 50 millivolt step is given. So like if what will be the rate of change? So if A is equal to 50 millivolts, A is equal to 50. Oh, sorry, this will have this times omega UGB. A is equal to 50 millivolts. Then what is dV naught by dt? 50 into 10 to the power minus 3 into whatever UGB is given. And what is the UGB? 1 gigaradians. That is 10 to the power 9. Okay. So this is 50 into 10 to the power minus 6. Correct? Sorry, 10 to the power 6. Now is this rate of change greater or less than the slew rate given?
Lesser.
Lesser, right? So the slew rate will never get hit. Is this clear? Because this is the maximum rate of change. At t equal to 0, maximum rate of change will occur.
Yes, sir.
And beyond t equal to 0, this rate of change will keep on reducing actually. Because this is related to e to the power minus t omega UGB, right? Is this clear?
Yes, sir.
Okay, so that means to say that your rise time, so the output voltage will be governed by this equation only. Okay, if the maximum rate of change also is lesser than the slew rate given, then the output voltage will be governed by this equation only. So in this equation, you will have to find out time at which this becomes at which V naught becomes point 1 times A, and at which V naught becomes 0.9 times A, and subtract those times to get the rise time. Is this clear?
Yes, sir.
Okay. So what is even for the maximum? For 100 millivolt also you can see till 1 volt also. At 1 volt, what will be the rate of change? dV naught by dt max will be equal to 10 to the power 9. Correct. So for 100 millivolt and for 50 millivolt, there won't be a problem. This particular equation will be used to find out rise time and fall time. But for 1 volt, the maximum rate of change that it is asking is 10 to the power 9. Correct? At t equal to 0.
0.5 into 10 power.
No, no, 0.5 into 10 power 9 is the slew rate, right? But from this equation, what is the maximum rate of change it is asking from the op amp? It is 10 to the power 9, right?
From which equation, sir?
From this equation, so this is the rate of change from the linear equation of the op amp, right?
Okay.
Yeah. So this is basically 10 to the power 9. So this is greater than the slew rate of the op amp. So op amp can't rise with 10 to the power 9, whichever this linear part is asking, it can't rise with that. So how it will rise is, it will rise as this slew rate equation. Okay, so it will basically rise as zero point 0.5 into 10 to the power 9 times t. Okay, is this clear?
Okay, sir.
Okay, and it will rise like this till the time till the time the voltage reaches zero point 0.5 volts. So after the voltage reaches zero point 0.5 volts, in this particular equation, what will happen? So basically, what you need to do is, you need to do the following. So let's say the linear part of the equation was dominating. So if the linear equation of the op amp was followed, so voltage would have risen like this. Okay. If the non-linear part of the equation was followed, voltage would have risen like this. Okay. Now, what you need to find out is what is this point. Before this point, the rising of the voltage will be according to the slew rate times the t, and after this point, the rising of the voltage will be according to the this equation that a times 1 minus t by rc, or t times omega egb. So you need to find this intersection point and like calculate this time, and after that whatever time is left to reach zero point 0.9 times a, you have to calculate that separately. Is this clear?
Okay, sir.
Okay. Any other doubts?
No.
Okay. So anyone else has any problem that needs to be discussed? Okay. So if there is no problem, let's solve a few questions. So this week was related to transfer functions, right? So we will see. You guys are familiar with second order transfer functions? Like you guys might have taken course on control systems, right? Do you have any experience of control systems? So who all have taken courses on control systems? Can you guys comment in the chat window? Okay. Let's see. Okay, some of you have taken it. Okay, so let's see what we are coming at. So let's try to find out the transfer function of this particular circuit. This is input and this is output. Okay. So first of all, can you quickly tell me what is the order of the circuit? Guys, if you answer, I will at least know that you guys are paying attention, and it will be better for me as well and for you as well. So if this session is interactive, it will be better for both of us.
Second order.
So second order, right? So basically, let's try to solve it and verify that it is a second order circuit. So this node, let's call it as V1. So you can apply KCL at this node. So what you will have is V1 minus VI by R1 plus V1 times SC1 plus V1 minus V naught by R2 is equal to 0. So let's arrange the terms. What we have is V1 times 1 by R1 plus 1 by R2 plus SC1 is equal to V naught, sorry, minus VI by R1 is equal to V naught by R2. Correct? So let's call this term as some RP, 1 by RP. And what is it equal to? 1 by R1 parallel R2. Okay. So if we simplify it to that, so what we have is 1 plus SC1 times RP divided by RP minus VI by R1 is equal to V naught by R2. Okay. So this is equation 1. So we will write KCL at output node as well. So what we have, V naught minus V1 by R2 plus V naught times SC2 is equal to 0. This is KCL at V naught. And this one is KCL at VI. So what we have now is V naught times 1 plus SC2R2 divided by R2 minus V1 by R2 is equal to 0. Correct? So what you can do is from equation 2, you can write V1 as V naught times 1 plus SC2R2. So you can substitute it to equation 1. What you get over here is V naught times 1 plus SC2R2 times 1 plus SC1RP by RP. So you will have minus V naught by, just a minute. Uh, Correct. Okay, minus V naught by R2 is equal to Vi by R1. Okay, so if you expand this, so what you get is 1 plus SC2R2 plus C1RP plus S square C1 C2 R2 RP divided by RP minus 1 by R2 is equal to Vi by R1. Is this correct? Uh, there is some problem in this, I think. Just a minute. Okay. Okay, fine. So we have this. Now what we have is V naught 1 by RP plus, sorry, minus 1 by R2 plus SC2R2 plus C1RP by RP plus S square C1 C2 R C1 C2 R1 RP, RP and RP in the numerator and denominator gets cancelled, right? This is equal to Vi by R1. Okay, now 1 by RP was equal to 1 by R1 plus 1 by R2, right? So what we have over here is V naught times 1 by R1 plus SC2R2 plus C1RP by RP plus S square C1 C2, sorry, this is R2 is equal to Vi by R1. So if R1 is taken common on both sides, you have V naught by Vi as 1 upon 1 upon S square C1 C2 R1 R2 plus S RP by R1 times C2 R2 plus C1 RP plus 1. Okay, so let's try to simplify it a little more. We have R1 over here and RP over here. So what we get from this is S square C1 C2 R1 R2 plus S times uh, C2 times R1 R2, and what is 1 by RP? 1 by RP is basically 1 by R1 plus 1 by R2, right? So this is equal to R1 plus R2 by R1 R2. Okay. So if we simplify this, so R1 R2 by RP is R1 plus R2. Okay. So we have R1 plus R2 plus C1 times R1 plus 1. Is this clear? Clear till this point, folks? So this is a second order transfer function, right?
Yes.
Okay, so you guys have studied about finding the time constants for individual resistors, for individual capacitors in a second or in a transfer function in this week's course, right? You guys have gone through the lectures of week 3, is it? Anyone? Okay, if not, then basically what we do is, so for low frequencies, so for let's say when let's say let's try to verify this, that whatever we have written is correct or not. So how can we verify at s equal to 0? At s equal to 0, what will happen? The gain from input to output will be according to this equation.
Maximum.
Yeah, but what is that?
1.
1, right? And even if we look at this circuit, so at DC, what will happen to the capacitors?
Open circuit.
Open circuit, right? So basically, this will add DC. This will look as R1, R2. So here is input, here is output. So since there is no place for the current to flow, so input will be equal to output. So we have verified to some extent that whatever we have written is correct. Okay, V naught by Vi. Now, once this is verified, so what will happen if, let's say, the frequencies are very small? So, if S is tending to 0, that means at very small, very low frequencies, which term out of these can be neglected?
Can you repeat the question, sir?
So, so basically, you have S square, you have S, and so you have three terms in the denominator, right? So, if S is tending to, okay, first of all, S can be replaced by j omega. This everyone knows, right? So, if omega is tending to 0, which term out of these three terms can be neglected? Or if S is tending to 0, which term out of 1, 2, and 3 can be neglected?
One and two.
Is it?
Yeah, 1 or 2, but let's say 1 and 2. Okay, but let's say, okay, out of 1 and 2, which is the smaller one? 2, no, no. Minded, this is S tending to 0. So for very small values of, for very small quantities, higher orders are smaller than the lower orders, right? For example, square of 0.5 is 0.25, which is smaller than 0.5, correct? So S square term will be smaller than S term. Okay, so 1 can be neglected. So if you wanted to make a first order approximation of the transfer function that we have written above, you can basically neglect this second order term, and you will be left with approximately S times C2 times R2 plus R1 plus C2 times, sorry, C1 times R1 plus 1. Okay, it's clear till this point.
So, what is the use of this approximation?
Okay, so what I'm getting at is, let's say you want to find so let's say you have been given a step, or maybe a slow varying ramp to this thing, and you know the frequency components are not very high in this. So what you can, any circuit can be approximated as its first order equivalent as equal to S times uh, 1 by tau 1 plus 1 by tau 2. There are multiple, how many energy storing elements are there in the circuit? As many time constants will be there. So if you have this approximation, you can approximate the values of, so naturally solving a second order transfer function is tougher, right? And maybe the second, since the, you know, the input to the system is not a very high frequency signal, so this particular approximation will also suffice. Now, if this particular approximation suffice, so basically what you can do is, you can put this, you can quickly write this approximation instead of going through all the hassle that we went. I will show you how. So you basically have this circuit, right? So this circuit is present with you. This is input, this is output. So across each capacitor, what is basically time constant? Time constant is 1 by RC, right? So what happens is you have to find out equivalent resistance across each capacitor by making rest of the capacitor zero, and that will basically give you the time constant for, to charge that particular capacitor. Okay, so if you do that, what is the, so let's find out R equivalent of for C1. So you will make C2 as 0. So how will it look? Vi input source will be de-energized. This will be R1, and you have to find out across C1 you have to find out. So C2 you will make as 0. So this will be just a floating node. Okay. So what is R equivalent? The R equivalent basically is equal to R1
R1
only,
plus
right?
R2.
No, no. This is a floating node. It won't be R1 plus R2. R2 won't come into picture, right? Because one side of the R2 is open circuit. And what is the R equivalent of C2? R1, R2, C2. So R equivalent is equal to R1 plus R2, right? So now looking in resistance over here is R1 plus R2. So as I said, you can write this as 1 by S times 1 plus tau 1 plus 1 plus tau 2. There are only two capacitors, right? So this will be equal to S times C1 R1 plus C2 times R1 plus R2 plus 1. Correct? So this is the same expression as we had it over here, right? Is this clear?
So while calculating C1, why we won't connect the C2? Why we won't short circuit the C2?
So, while this is a procedure, more of a procedural thing rather than intuitive thing. So, what we do is so you can remember this just as a procedure. So, while you are calculating the equivalent resistance of one particular capacitor, you will make rest of the capacitors as equal to zero. I mean, I don't have an intuition for that as of now. I can look that up. And if there is any intuition that exists, I can update you for in the next class.
For inductor, it is quite opposite.
Yeah, correct. For inductor, it is opposite. Other thing, a slight amount of intuition you can get is because since we are anyways interested in very low frequencies, so at low frequencies, the capacitances are mostly high impedance, right? So
At DC analysis.
yeah, at DC and at frequencies closer to DC, the impedance of the capacitors will be very high, right? So basically, you will open circuit all the capacitors and short circuit all the inductors.
Okay.
Yeah. So this is how basically you find out first order approximation to any some nth order circuit. And where is this useful? This is basically useful to find out. Let's say you need to find out approximate response for the step input, which will be equal to 1 minus e to the power minus t by rc minus t by some 1 by tau. So, this will give you roughly what is the rise time fall time. Instead of exactly finding out what will be the rise time fall time, you just need a rough approximation for that. So, in these kind of situations, you can use this approach. Okay, let's try to build some more insights over this particular equation that we had. Okay, so can you guys are you aware of second order standard second order transfer low pass transfer function, how it looks generally? Okay, so if some of you might have taken control system, so you would have studied that a standard second order transfer function looks as follows: s square by omega naught square plus s by omega naught q plus 1. Okay, and how does its frequency response look? At DC, you will have 1, and basically it falls like this. At high frequency, it will fall by second order roll off, that is minus 40 dB per decade. Now, what is this omega naught? So, what will be the gain at omega naught? Can anyone find it out? Of the second order transfer function that I have written over here, what will be the gain at omega naught?
0.707. That is 3 dB.
No, I mean, are you sure? From give me the value based on this transfer function that I have written over here.
1 divided by R1 omega naught square is equal to 1 divided by R1 C1 R2 C2.
No, there is no R1 C1 R2 C2 over here, right? Uh, uh, Based on this particular transfer function, just tell me what is okay. You understand these terms, omega naught q. Are you familiar with this? Have you ever seen these terms? What does q stands for? Quality factor, you guys know? Okay, no issues. Just tell me what will be the gain at omega naught. So, what you will replace s by j omega, right? So, if you replace s by j omega, this transfer function h of j omega will be equal to 1 by minus omega square by omega naught square plus j omega by omega naught q plus 1, right? Now, if you substitute omega equal to omega naught, what you will get? Minus omega naught square by omega naught square plus j omega naught upon omega naught q plus 1, right? So you get gain at omega naught as minus j times q, or the magnitude response as q, right? So this in the magnitude response, this gain will be q, correct? Is this clear? Okay, so I hope it is clear till this point. And now let's see, let's try to find analogy between the transfer function that we have got from the circuit that we have made and the transfer function that we have written over here, the standard second order transfer function. Let's try to find out the analogy between them. So based on these two equations, what is omega naught in our circuit that we have written? What is the value of omega naught?
C1, C2, R1, R2.
Uh, are you sure? So basically 1 by omega naught square is equal to C1, C2, R1, R2, right? So omega naught is equal to,
1 by root of C1, C2, R1, R2.
correct, 1 by square root C1, C2, R1, R2. Okay. So what is the second term? So second term basically, I will write it over here. 1 by omega naught q is equal to C2 R1 plus R2 plus C1 R1. Correct? So what is the value of q you get from here? 1 by omega naught C2 R1 plus R2 plus C1 R1 is equal to q. So if you substitute the value of omega naught, what you get over here is R1 plus R2 times root C1, sorry, C2 by C1 times square root R1 R2 plus 1 by square root, sorry, this is C1 by C2 times R1 by R2. This is the value of Q. Okay. So can you simplify it a little more? Let's try that out. We have R1 by R2 times C2 by C1 plus R1, sorry, R2 C2 by R1 C1 plus square root of R1 C1 by R2 C2. This is equal to the quality factor of whatever circuit. So Q is basically denoting the quality factor. And what is it? The gain of so the magnitude response of your second order transfer function at omega naught. And omega naught is called the central frequency. Okay. So now let's say, as Vinod pointed out initially, that let's say we want our 3 dB bandwidth to be equal to central frequency. So what quality factor we need to have?
So can you repeat the question?
So let's say the 3 dB bandwidth. So at 3 dB bandwidth, what is the gain of any magnitude in the magnitude response? Do you know this?
0.707.
0.707 or square root 2?
Root of 2.
1 by square root 2. Okay. Gauri, is this clear?
Yes.
Yeah. Let's say I want, let's say, so basically Q I want as 1 by square root 2. Okay. So if I want that, what I will need is square root R1, R1C2 by R2C1 plus R2C2 by R1C1 plus R1C1 by R2C2 should be equal to square root 2. Correct?
Yes.
Okay. So let's try to open this up. So what we get is 2 is equal to R1 by R2, C1 by C2 plus R2 C2 by R1 C1 plus R1 C1 by R2 C2 plus 2 times these factors, right? So the first thing we will have, so multiplication of these two will give 1. So basically
So the first term is R1C2 by R2C1.
R1 just, oh sorry, R1 C2 by R2 C1, correct. So okay. So the piecewise this thing like their multiplication will give us R. So this will come out to be C2
C2
by
by C1.
C1 plus R1 by R2 plus 1. Right? Is this clear? So from here, what do we get? R1 C2 by R2 C1 plus R2 C2 by R1 C1 plus R1 C1 by R2 C2 plus 2 times C2 by C1 plus R2 by R1 plus 2 is equal to 2. Right? Clear till this point?
Yes.
Okay, so basically this so 2 and 2 can be cancelled. So basically this term is equal to 0, right?
Yes.
Okay, and now do you think this can be 0? All the resistors and capacitors will be positive quantities, right?
Yes.
So can there some multiplication, division, addition can result in a quantity equal to 0?
Yeah.
Is it? Are you sure? So can any combination of R1, C1, R2, C2 result in this term becoming 0?
At negative frequencies.
What?
When the at negative frequency range.
No, there is no frequency range over here. These are all values of resistances and capacitance. There is no S in this. You can see that, right? There is just component values. There is no omega in this. So for this to become zero, at least few components you will have to have negative values, right?
Yes, sir.
So that is not physically possible, correct?
Yeah.
Okay. So what a maximum quality factor this can give you? This term always will be greater than zero, right?
Obviously.
Okay. So if this is greater than zero, and basically this, what is this equal to? 1 by q square, right? So this plus 2 is equal to 1 by q square, correct?
Yeah.
Yeah. So if this term should be greater than zero, then 2 plus, so let's call this term as some k. 2 plus k should be greater than 2, right?
Yes, sir.
Okay. If 2 plus k is greater than 2, that means to say 1 by q square must be greater than 2. And if that is the case, q square is less than 1 by 2. That means to say q is less than 1 by square root 2. Is this clear?
Yes, sir.
Okay, so this circuit, no matter what combination of resistors and capacitors you take, cannot give you a quality factor greater than 1 by square root 2. Okay.
Okay.
Okay, so what the okay, but it's not okay, but we can't say that okay, it can't give you greater than 1 by square. What if you want that? What will you do then? So basically, any passive circuit consisting of only resistors and capacitors can never give you quality factor greater than 1 by square root 2. This is for sure. So what is the, apart from resistors and capacitors, what other element do you know? What element we have not used in this?
You tell it, sir.
Inductors, right?
Yeah.
So let's try to find out another circuit. Let's try to figure out what is. Let's see this circuit over here. Okay. So is it a low pass transfer function? At very low frequencies, what will be the output?
1.
1, right? Because L will be open circuit, capacitor will be short circuit. So at very low frequencies, you will have quality factor equal to, the gain equal to 1. Now, at very high frequencies, what will be the gain?
0.
0. So it basically satisfies your low pass transfer function characteristic. Now let's try to find out what exactly the transfer function is. Okay, we will try to find that out. So what we will do is, uh, So what we have over here is we will try to we will put the resistor divider. So one impedance division rule. So 1 by SC. So V naught by Vi will be equal to 1 by SC divided by R plus SL plus 1 by SC. Right? This is clear, right? Okay.
Yes, sir.
So if you simplify this, what you will get over here is S square LC plus SRC plus 1 is equal, this is the transfer function. Okay. Now, what you have over here is, so if you again compare it with the standard transfer function that I wrote, so you have S square by omega naught square plus S by omega naught Q plus 1 is your transfer function, right? So if you compare with that, omega naught you get as 1 by square root LC. What is quality factor? 1 by what is 1 by omega naught Q? That is equal to RC. So from here, what is the Q that you get? R times square root C by L. Okay. So here, basically, here you can clearly see if you increase the resistance. No, wait, there is some. Oh, sorry. It will be 1 by R root 1 by R square root. Sorry, 1 by R square root L by C. So here you see, let's say if you want a quality factor of a very high, let's say you want a very high quality factor, more than square root 2 or equal to square root 2 also. All you need to do is reduce this R. For given L and C, you can reduce this R to get whatever quality factor you want. Is this clear?
Yes.
Okay, so if you have inductors in the circuit, then you can make a low pass filter with any quality factor. Is this clear?
Okay, sir.
Okay, now another big question is how do you get, how do you, so in discrete components, inductors are available. But what happens in, so inductors, you know how inductors are made, right?
Yeah, magnetic coil.
Magnetic coil. But let's say you want to have an inductor on a integrated circuit. You have seen integrated circuits, right? In your DP also there is an integrated circuit made.
Yes.
Okay, so integrated circuits are very small. In that, putting magnetic coil and all is a very huge, very tough task. It's very difficult to put a magnetic coil inside a integrated circuit. So, what do you do in case of integrated circuits where you want inductances? So, there we use actually the op-amp based circuits in order to emulate inductances. So, we will see how. So let's see how an inductor can be emulated. Emulation of inductor. Okay. So okay. So before that, before we actually go into emulation of inductor, just a minute. Okay. Yeah. Let's figure out how do you emulate an inductor. So if there is an inductor of value L and you apply a voltage across this, what current should flow from here?
1 by L integral of V dt.
No, no. Okay. Let's talk in terms of Laplace. V by SL, right?
Yes.
Yes.
Okay. V by SL will flow. So, and the same current will flow from here. So somehow, with use of op amps and this resistors and capacitors, we will try to emulate, see if V by SL is possible or not. Okay. So this is a floating inductor in which both the nodes are accessible. Uh, if let's say the inductor was grounded, so and you apply V on one side, so what will you get on? So what current you will get? V by SL, right? So we will see if this is possible using a simple circuit. Okay. So you need you need somehow to somehow make sure that the current that you are sourcing, current that is flowing from so whatever circuit this is, the when you apply a voltage V over here, the current that should come out should be inversely proportional to the frequency. This is what you need to make sure, right? So let's see how we can do that. If you apply a voltage of V over here and you take so for that basically let's introduce one more component, that is a transconductor. So you know about MOSFETs, right? You have studied about them, right? So transconductor, how it works is, if input is Vi, what will be its output? And this is Gm.
GMIGS.
Sorry, the current. So basically, what does a transconductor means is, so if we have Vi over here, GMVI is there at this node, and the output that basically comes out is GM times Vi. Okay.
Yeah, sir.
Okay. So let's say this block is available to us. So how can we make inductor using this particular block? A transconductor. We'll see. So if V is applied to a transconductor with a value of Gm, what will be the current that will flow from here? This current will be V times V by Gm, right? So if this is V by Gm and it is pushed into a capacitor, what will be the voltage developed at this node?
So why can't it be GM into VI?
Sorry, V. Sorry. It will be V times Gm only. Gm times V. And if Gm times V is pushed into the capacitance, so what will be the voltage developed at this node?
One by C integral of GM V dt.
In
GMV by
Laplace,
SC.
GmV
GMV
by
by
SC.
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 Yeah.
Yeah, in Laplace domain, it will be GmV by SC. Now this is basically proportional to inverse of the frequency. Now somehow we need to convert it back to current, right? Is this clear?
Yes.
So, how can we convert it to current? Voltage to current, how do we convert? Using a transconductor, right? And where do we want this current to flow from? From the output. So, if we have a negative transconductor, or okay, if we have a transconductor of value minus gm and connect it like this, so what will be the current flowing from here? What will be this current?
GM into V.
Gm into, no, gm into v is this current. So input, what is the input voltage for this transconductor?
GMV by SC.
GMV by SC is the input voltage to the transconductor. So if the voltage is GMV by SC, what is the output current?
GM square V by SC.
GM square V by SC, correct? And it will flow in
Yes.
the opposite direction because the transconductance is minus GM. So GM square V by SC. Now, what if there was a inductor connected to ground over here? What will be the current that will be flowing from here? This will be V
V
by
by
SL.
SL.
Okay,
Yes.
so if you compare, no current can flow in this direction because the transconductance is basically voltage controlled in current source, and if you are measuring the voltage, your impedance will be infinite, right? So what will happen is no current will flow in this direction. All the current of Gm square V by SC will flow in this direction. So if we compare this circuit and this circuit, what you get is L is equal to Gm square by C. So this particular circuit over here is called gyrator, and it is used to emulate inductances without actually making the magnetic coils. Is this clear?
So can you explain the last part?
Which part? Till what point you understood this?
Sir, input is GM by GM V by SC. How did you get that?
Sorry, the input to the second transconductor, the input to the this transconductor is GMV by SC,
Yes.
but like here it's V only, right?
Now, how did you get, sir? GM V by SC.
So GMV by SC we got, basically we have voltage V over here that will result in a current of GM times V in this direction. Now this current can't flow over here, right? Because this is infinite impedance. All the current will flow in into this capacitor. Now, if a current flows into a capacitor, the voltage developed is I by SC, right? And if I is GMV, so the overall voltage developed at this node will be GMV by SC.
Okay, sir.
Okay, Gauri, what part exactly you wanted me to explain again?
Yeah, the last one, sir. Inductor part.
Okay, now, here you understood, right? If you apply a voltage V to this particular circuit, what will be the current that will be flowing from this node?
GMV.
No, no, this particular node,
GM square V by SC.
GM square V by SC. So if there is a voltage source over here of voltage V, the current flowing will be GM square V by SC. Is this clear?
Yeah, sir.
Yeah. Now, if I had connected the same voltage source to an inductor of value L, what will be the current flowing from this voltage source? What will be the current flowing from this voltage source?
V by SL.
V by SL, right? So this and this both are inversely proportional to frequency, right?
Yeah, sir.
Yeah. So that's so if we compare these two, so this complete circuit will behave as an inductor to which you are applying a voltage source V, and that inductance value will be Gm square by C. Is this clear?
Yeah, sir.
Okay, now you guys try to figure out. So you know that the circuit exists that is called gyrator. How you will use this circuit in a combination of R and C to make a low pass filter with a quality factor of 0.707. Okay, try to figure this thing out. If you are able to do that, great. Otherwise, we will discuss it in the next tutorial. Clear?
Okay, sir.
Okay. So, any other doubts?
Hello, sir.
Yeah, yeah.
One doubt I have very simple. What is the difference
Okay.
between loop gain and closed loop gain?
So, closed loop gain is okay. I will explain it over here. So, here we have the feedback terminology, right? So, how does our feedback system look? So, we have some gain, we have some beta over here, and we measure the negative. So this is how feedback system look like, right?
Yes, yes.
Okay. So closed loop gain is gain from input to the output when the complete loop is closed, and loop gain refers to, let's say you have broken the loop, then you if you are given an input over here, let's say some test, what will be the gain from here to here when the output is given as 0. So this will be equal to G times beta, the loop gain, or minus
Okay,
G
sir.
times beta. Okay, the loop gain, basically we can remove the negative quantity. So basically this will be equal to G times beta. But the closed loop gain will be from input to output, and that will come out to be what that will come out to be
G dividing by 1 plus G beta
1 plus G beta. So
or
this is your
negative
closed
feedback.
loop. Yeah, this is your closed loop gain, and your open loop gain is basically, or loop gain to what we refer to is the overall open loop gain that you have in the complete loop of the negative feedback.
Yes, sir. Got it, sir.
Yeah. Any other doubts?
Sir, irrespective of the open loop gain in the op amp, whether
Yeah.
the that closed loop gain it will be same always for irrespective of the open loop gain.
No, it won't, right? As long as your gain is very high, so let's say this G is tending to infinity. In that case, your closed loop gain will become 1 by beta, correct?
Okay, okay, yeah.
Then it won't depend. But if your G is not very high, the forward gain is not very high, or overall G times beta is not very high, in that case, it will depend on the open loop gain also.
Okay, sir. Okay, fine, sir. No doubt is clear. Yeah.
Okay.
Thank you, sir. Thank you, sir.
Yeah. Any other doubts? Okay, so if there are no other doubts, this was it from today's session. Thank you everyone for attending.
Thank you, sir.